Good morning, everybody, again. Thank you for showing up. It's great to see so many people show up today for our little adventure. I envision this course more as an informal exercise to show you how you can quantify some of your savings. So if you have any questions as we go along, please feel free to raise your hand and ask them as we go along. You don't have to be afraid to interrupt my train of thought. There isn't much there, so let's just get it on. We'll call this workshop as Quantifying and Prioritizing Opportunities in Industrial HV. A couple of things that I'd like to point out in this is, first and foremost, industrial HV, which is slightly different than what people usually refer to in heating and ventilation for commercial buildings. Most of that difference lies in the fact that, as you're all familiar, industrial buildings don't operate and don't behave anything like commercial buildings. The focus on what they're supposed to do is different than what the commercial building is supposed to do. There's very little, if any, consideration for comfort of occupants outside of basics. And most of the reasons why we do heating and ventilation in the building is A, not to freeze anybody, and B, to ventilate whatever we have in the process in the building, which is drastically different than in a commercial setting like this one. We would quickly notice that temperature in here rises, and we would complain about makeup air not working. Whereas in the industrial building of 200,000 square feet, if one of your 3 makeup air units dies, you would have a hard time somebody actually noticing it for a while. So we behave and we work under different rules, and we would like to highlight that. So when typical vendor will come and say, well, I've done so many commercial buildings, that doesn't necessarily mean that they're known and know what they do in industrial HV building. So feel free to ask them questions, how many installations they have in actual industrial setting before you commit to anything. Today's topics, what we're going to cover is, we'll go over our programs, Enbridge programs for industrial customers. Most of you are familiar with them, but we'll just do a brief synopsis, run through them. We'll do the whole topic of this presentation will be sort of like a case study of imaginary facility that we created here for you, just to show you how you would do a typical building in your particular environment. We'll go through identifying opportunities. We'll prioritize them based on the cost-benefit ratio. And we'll talk a little bit about action and implementation. And as I said, feel free to ask any questions as we go along. So let's start. Industrial programs for our Enbridge customers have been around since the mid-90s. We have hopefully gained customer trust through our actions and through our results that we developed with you. And on top of that, we have auditing process in place, internal and external, that ensures that our calculations are as accurate as possible, given that we only work on engineering calculations. So unlike some of the other programs, our programs are structured in such a way that we do a very closely monitored calculation of the savings, and we incent people on calculated savings and estimated savings, rather than making you wait a couple of years before we monitor and verify all the savings. So this is going to be familiar to most of you folks who work in industrial facility. It's essentially basis of any lean manufacturing, world-class manufacturing, whatever we call it. It's a plan, do, act, check list, and it starts, of course, with the knowledge development. We try to develop knowledge for our customers, and this workshop is one such activity, to essentially arm you with information. So you can ask intelligent questions of your vendors, of your peers. Why do we do certain things, and how can we improve on what we do? Then we help you with opportunity identification. We can help you with testing. We can help you with energy use analysis. We can provide incentive for you to have a third party do the testing or energy use analysis. Whichever way works for you, we're fairly flexible, but we want you to get information in front of you so you know what you're working with. Measurement, of course. We have programs that help you with implementing your measurement and targeting systems, your measurement verification systems. As long as there's a component that you're going to use this information to actually implement energy efficient projects, we will help you with those costs. Engineering analysis. We have a group of 10 very capable engineers on staff. All of them are engineers. All of them can do very good calculations of energy savings for you. And feel free to take the advantage of this free service so you can have an engineer working with you for a while at no cost to you. Last is, of course, action and implementation. This is the only step that is really up to our customers, up to you. We cannot do that for you. You're the ones who actually have to sign the requisition and implement this, whichever action you decide to do based on energy efficiency studies. However, we hope that the rest of the steps actually helped you make that decision as firm as possible and arm you with information so when you ask for money, you actually get back the payback that you were expecting. So this is what we have done, our little group of industrial ESCs. We have saved roughly 110 million cubic meters of natural gas, slightly over 20 million kilowatt hours of electricity, and 800,000 cubic meters of water in the last 3 years alone. And of course, if you translate that, that saves you CO2 emissions and improves your bottom line. It's one of the feel-good saving measures of the day because you don't have to push your vendors for a lower price. You don't have to push your labor for a lower price. You get benefits of the savings without actually getting anybody upset. So this is going to be our test facility for today. We called it Improve Global. Let's say it looks something like this. It will look very familiar to all of us who have spent most of our lives in the facilities. Myself, I come from industrial background. I used to be in design engineering for 10, 12 years. I helped start up a company in China after that, and after that, I worked for 7 years as a capital project manager in automotive industry in tier 2 supplier. So this facility is pretty generic, and I think all of us will recognize some elements of it. But what we really want you to focus on is facility operations. So for this particular case, let's say we all work for this facility. So we work about 5,760 hours per year operational, which means production is running those hours. We use, let's say, 861,000 cubic meters per year, 196 kilowatt hours, 70 degrees F intertemperature, and our facility location dictates that we have about 4,300 hours of heating season, which is typical for Toronto area. And the facility's square footage is about 200,000 square feet. So let's work at this facility for the rest of this workshop. One thing I would like to point out, out of these 2, 4, 6, 7 parameters, 5 of them are essentially within your control. So you always hear, well, I can't do anything, this is not within my control. 5 out of 7 is within your control. Don't think that energy is not within your control. It is. So let's peek underneath. Let's try to find out what this facility is actually, how does it operate, where it can be improved, and how to identify opportunities. So you will have often either vendors, peers, people with ideas that will come up and they will say, okay, well, we have this infrared heating, we have direct fired space heating, we have process oven heat recovery. Why don't you do something and save some energy for us? And then, of course, once that comes up, there's other things that your brain probably says, oh, maybe there's some other ideas we don't even know about, we haven't heard of. So how do you actually make sense of all this information, if you will? So first of all, let's establish some rules. Let's say that quantifiable benefits make better business cases. I think that all of you will agree with that. If you can measure something, you avoid later going with a request for a $150,000 investment and accountant is asking you, and how much money are you going to make us back? So you want to know effectively what you're going to save, because that will improve your chances of being approved. All of us worked in this environment, all of us have asked for money, and in most cases, people are like, well, I have 10 projects on the go. Which one should we give the money to? So we want to make your project the most quantifiable, the best project looking, so you get the money rather than some other projects on the go at the facility. And we as ESCs here, our group of engineers can actually help you in that goal. So we're here to help with opportunity identification. This is the area we are focusing on today, with testing and energy use analysis. Often you will have questions for yourself and for others to answer. Okay, I want to replace a heater that's burnt out. I want to replace a makeup air unit. And they will ask you, well, how much energy are you going to save? To know how much energy you're going to save, you need to know how much energy you're actually using in that unit alone. Often you will have people come to you and say, I'm going to save you 20% energy. 20% of what? 20% of overall energy, 20% of seasonal energy, 20% of that unit's energy. What is 20% based on? So that's the first question you should ask anybody who talks to you about savings. 20% of what? So of course that will lead to some sort of measurement. Sometimes you can do measurement by quantifying some key energy inputs. Sometimes you have to choose the proper metering method to measure whatever it is that you're interested in achieving. Of course, our ESCs have experience and they can help you, guide you in that decision. You can engage any of your usual vendors that you work with. You can have a number of people help you. You don't have to make that decision yourself. So in our improved global facility, let's say this is our bill, yearly consumption bill. You can do this yourself by looking at your billing data over the last 12 months. Easiest and best way of doing is to contact your particular energy solutions consultant at Enbridge, because we have your consumption history. What we do is we do this type of graph for you based on last 3 years. So we average any changes in your production levels from year to year. So let's say this is what it looks like. Now let's separate on this bill. In the last workshop we talked about seasonal versus process usage. So we'll skip this. If you're interested, there will be a webinar about that particular portion posted shortly on our website. But for now, let's just say that to determine process versus seasonal energy usage, we'll take the 3 months in the summer, June, July, August, that in Toronto is typically not a heating season. So therefore, we assume that there is no heating load on those 3 months. So you mark those 3 months as your base, and then you extend that line across to get what you call a process load. This is a load that is dependent on whatever it is that you're working on making your product, because it happens all year long. So that's that basic level. That's a process load. In this case, it's about 168,000 cubic meters per year. The rest of the load is what we call a seasonal load, because it depends on the weather and what time of the year it is. It's high in the winters, very low and non-existent in the summers. In this particular facility, we have 693,000 cubic meters of gas being used on seasonal load. So when you talk heating and ventilation, more often than not, this is the number you work with. Not 860,000, this is the number you work with. So now that we have identified natural gas users, how we separate them? We already talked about, we have something called seasonal and process load. No surprises, seasonal load is comprised of makeup air, space heaters, while the process load in this particular facility, because we have one furnace, is process oven. So let's take a look at the makeup air. Those are these blue units up here. In this case, we have 2 units. What does makeup air do? If you have any process that requires you to exhaust air to make your indoor air quality satisfactory to the rules and regulations, you have to make that air up somehow. And you make it up typically through the makeup air unit. This will be to simplify matters. This facility will only use regular makeup air. There won't be any humidification. There won't be any recycling of the air. It's just 100% outdoor air makeup air units. But this is what I would really like you to focus on when you look at makeup air units. This is the basic design of the makeup air unit. And it consists of intake of the fresh outdoor air at outdoor temperature. So you're pulling in a certain amount of CFM at outdoor temperature. You put it through the filter and through the burner, where you add some energy burned through natural gas typically. These are usually direct fired makeup air units. You add some more energy to spin the fan that then blows the heated air into your indoor of the facility. So that's the makeup air. That's the basics of it. So if you look at it that way, it's fairly easy to quantify how much makeup air unit will use in energy. As we go along, we will use, as I said, makeup air, 50,000 CFM in this improved global facility. At typical outdoor temperature in our area, average is about 37.5 degrees F, which is about 3-4 degrees Celsius. And because it's a direct fire unit, it usually operates at about 90-91% efficiency. So in this case, we said we have 2 of them. Each is going to be identical, so 25,000 CFM each, similar efficiencies, and of course, same outdoor air conditions. So our first exercise will be to calculate this makeup air consumption. Usually, if you have makeup air, space heaters, and you want to know how much energy you use, I would usually start with the makeup air because that's the most clear-cut calculation, and it's pure physics, so it's very hard to make it a wrong decision based on that. So you have in your work activity workbooks at exercise 1, I believe you have this formula. This is the basic formula for calculating heating of the air, of any source of air. Effectively, it says that the energy in BTU per hours is 1.08 times CFM times delta T divided by the efficiency of the unit. 1.08 comes from converting cubic feet per minute into the hours and dealing with the specific heat of air and the density of air. So that's just the conversion factor. So if you remember that formula, you'll be able to calculate anything that has to do with the heating of the air. As we said, as a reminder, we had 50,000 CFM. We have 37.5 degrees outdoor temperature and unit efficiency of 91%. So if you would, please take a look at your exercise book, and if you could try to calculate based on these inputs, what do you get as your output in savings? The second step, it is because the delta T went from 70 to 37.5, and then 50,000 CFM. And then we have to convert from this energy to get natural gas, volume of natural gas. We use something called higher heating value of natural gas, which for Enbridge territory is roughly about this 35,844 BTUs in every cubic meters of natural gas. So you divide whatever BTUs you got, you divide them by 35,844. Over 4,308 hours of heating season, you should be getting somewhere around 231,000 cubic meters of gas, 232,000. Again, numbers are not critical. This is a made-up facility. All I want you to focus on is how to calculate the first formula, how to calculate the BTUs per hour, and how to convert that into natural gas, because every case will be slightly different. But if you just remember those 2 formulas and you take the activity book with you, you should be in a good shape to calculate most of your heating and ventilation needs in your facility in the future. So now that we dealt with the makeup air system, you calculate your need for makeup air energy, and you come up with a number, in this case 231,790 cubic meters of gas. The second portion of this formula, the second portion of what you have to always keep in mind, when you look at the facility and you have some process in it, in improved global case, we had a process oven. So you have to provide some sort of exhaust to exhaust the air, whatever it is that you don't want your people to breathe. And you have to provide makeup air to make up the difference that exhaust has sucked up. Therefore, your makeup air consumption should roughly be between 90 and 110% of your exhaust volume. But that's not always the case. It depends on your particular indoor air quality. It depends on your facility. But this is a good guideline. If that is not the case for you, ask why isn't. And if there's good reason, if somebody has done some indoor air quality and they need it, that's fine. But ask anyways, because this is typically how the units are designed to operate. The reason that is important to balance those two is infiltration air. People usually say, well, I have 100,000 CFM of exhaust, 20,000 CFM of makeup air, what's the big deal? Big deal is that because of the physics, and you're not isolated, there's no sealed facility, except pharma maybe, the rest of the volume of air between the exhaust, the difference between exhaust and makeup air will come from somewhere. And we call it infiltration air. It will come through your shipping doors. It will come through your regular doors. You'll have all sorts of problems with the air quality inside the building. People will usually feel fairly cold if your exhaust is much bigger than your makeup air. Because you have to remember, makeup air is heated to about 70, 75 degrees F. So at least it has some heat to it. Infiltration air, if you pull it through the shipping doors, I'm sure you guys all notice that. You walk by your shipping doors, and you feel cold because all that air, cold, unfiltered, unprepared air, just goes into the facility. And you cannot avoid it. There's just no avoidance. So that's why you want to balance exhaust and makeup air unit. So exhaust in this facility is drawn out in red. There's different exhaust, general exhaust, process exhaust, a couple exhausts there on the air compressors. So how do you calculate that? Let's say that this facility has 176,000 CFM of air. Remember, we had 50,000 CFM of makeup air. This one has 176,000 CFM of exhausted air. We'll assume that exhausted air is heated to 70 degrees F, which is your indoor set point. And we'll say that we have 3 fans running at 50,000 CFM, 1 fan running at 25,000 CFM, and we have oven exhaust exhausting about 1,000 CFM of air. So for the total of 176,000 CFM of air. So this next step will be to calculate how much energy could be in that air that we're exhausting out. That's the second portion of trying to figure out where energy is used in your heating and ventilation. So we calculated portion of the heating, because it's easy to calculate makeup air first. You find out your nameplate information on the makeup air unit. You multiply it by the difference of the temperature. You get your consumption. Now let's do the same thing for exhausted air. Formula is exactly the same. As I said, if you know this formula, you will be able to calculate a lot of your heating and ventilation needs in your facility. Formula is identical. 1.08 times CFM nameplate of all your exhaust combined, motorized exhaust, times delta T divided by the heating efficiency of the system. Now this time around, we'll use heating efficiency of the overall system because we're not just looking at makeup air units. We're actually looking at the whole system. We'll assume that in our improved global building, that heating system runs at 80% efficient. So if we do the same calculation that we did last time in your activity book, I'll give you a couple of minutes again, we should come up with the answer of how many BTUs per hour this exhausted air has. So if all is well, we should end up somewhere at about 7.7 MMBTU per hour. We used same higher heating value of natural gas, 4,308 hours, should give us about 928,000 cubic meter result. Okay. Now, if we paid attention and we said 928,000 is what we use here, what the heck happened to 693,000 that we're actually paying for? Are we actually using more than we're paying for? And I, as an Enbridge rep, can tell you, no, 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 no. For sure, you're not using more than what you're paying. So what's going on in here? There's a number of different things that can go wrong in this calculation, 2 of which you should be aware of. First, nameplate information. If you do the calculation based on your nameplate information of all your exhausts, you may find that A, not all of them operate the way you think they operate, and 2, they may not be as efficient as you think they are. If it says 5,000 CFM on it, it may have been 5,000 CFM a long time ago. Maybe it now runs at 500 CFM for whatever reason. Maybe a long time ago there was a belt that failed on that unit. We didn't have the proper shift, so we replaced the shift with something else, and it runs in completely different area of the operational curve of the fan than you think it operates. So that's one good check to say, wow, this number is significantly different than what I expect and what I'm paying for. So that's first check. Check the calculation versus what you're actually using. Second thing that can go on is we said that we have process oven in the place. In this particular facility, we have a process oven, we have no cooling. Let's say we process it, we put the things on the shelf at the back. Well, what does that do, really? If I take a whole bunch of, let's say, aluminum parts, I heat them in the process oven at 400 degrees F, and I put them on the shelf. They cool down, right? So what happens to all the heat between 400 degrees F and the room temperature? It gets distributed in your facility. So you have something called internal heat gain. And that goes for your lights, that goes for your process equipment, that goes for your motors. 90% of your electricity that you will use, if it's inside your facility, 90% of that energy will actually be returned back as a free heat, one way or the other. Unless you take these hot parts, put them on the truck, and get them out of the facility immediately, the heat will be retained in the facility. So we have something that we call internal heat gain. And we will deal with this in a little more detail in one of our next workshops. But for now, let's just say we get some nameplate information from the oven, oven operating parameters. You can calculate roughly what your internal heat gain would be expected. So we will not go through that exercise here. We will have a special workshop just that will deal with these issues. So let's just assume that this calculation is correct. We have some based on electrical loads, we calculated that total internal heat gain is equivalent of 183,000 cubic meters of gas. Okay. That's what energy that we radiate from or convect from our from all our parts gives back to us as free heat. So we take our seasonal load at 693,000 cubic meters, internal heat gain input, because that 183,000 cubic meters at heating efficiency of 80% is worth about 229,000 on the input side. We have to remember we had that 928,000 that we calculated, that was our target. When you combine natural gas seasonal load and internal heat gain input, we get about 922,000 cubic meters. So this is much closer. So now we start to recognize that, okay, we're not using extra gas. It's not terribly wrong with the calculations. We have a certain amount of natural gas that we use. We know 693,000 cubic meters. About 230,000 cubic meters comes out of the internal heat gain or free heat, for a total of about 922,000 cubic meters per year that we're exhausting if we exhaust all that air at 70 degrees F. Okay. First thing to note is then forget that calculation for exhausted air. Internal heat gain plus your natural gas seasonal load is what your base load should be. This is where you base your savings off of. The rest probably came from either underestimating some of the exhaust flows, some other errors, or what can happen is, if this is your overall exhausted air energy content, this is your metered seasonal load, consisting of makeup air consumption, space heating consumption, and internal heat gain. So that difference on the top could be very drafty environment. It's quite possible that you essentially, if you find that your exhausted air energy content calculation and the sum of these metered seasonal load plus internal heat gain has some gap, it's usually when you walk through around your shipping area, you'll find it very cold, and people will complain about the cold facility. What that means is that you're really not exhausting at 70 degrees F. You're pulling so much infiltration air in that doesn't have any time to heat up. It gets thrown out the exhaust at not quite the room temperature, but not quite the outdoor temperature either. Therefore, your energy content assumptions that all exhaust is 70 degrees F were wrong. And that's the time to look at, why is it so drafty? Why am I using so much infiltration air when I don't need? So let's now look at that third block. We talked about makeup air consumption. We talked about internal heat gain. Let's talk about space heating consumption. Things like unit heaters down on the bottom, or that big radiant tube at the shipping doors that people install on top of the shipping doors. Why am I talking about this the last? Because it's the hardest thing to quantify. Let me repeat that one more time. It's the hardest thing to quantify. You will have, in typical 200,000 square foot facility, you will probably have 30, 40 of these unit heaters of different shapes, different vintages, different generations. 3 are wired this way, 4 are wired that way, 4 come from some other facility that closed and they gave us their heaters. We have no idea. And to try to quantify how much each one of them is using is gonna be a significant portion of your career, and you don't have that time. So we're trying to deduce it from other calculations that are easier to do. That's why I'm doing space heating calculations last. So let's remind ourselves. We have makeup air and space heating that make up the total meter seasonal load of 693,000. We have internal heat gain. So our corrected exhausted air energy content consists of those 3 blocks. We know what the makeup air volume is because we calculated it. It's physics, and it's fairly easy to calculate. We know what your exhausted energy content is because we know what our internal heat gain is. So the leftover is space heating. That's the easiest way to formulate how much your space heating itself uses. We'll worry about it later, where each unit, how much it uses, but space heating itself should be using this much. And that brings us to our third exercise. It's space heating consumption. So effectively, we will go through this exercise where we take what our seasonal load is, what exhausted energy is, minus the internal heat gain, minus the makeup air consumption. It'll give us space heating. So we should have come up with roughly 460,000 cubic meters of gas. It's strictly the difference between seasonal load and makeup air consumption that we calculated earlier on. So now we have a number, 461,000 cubic meters of space heating. Now I'm going to throw a rule of thumb at you. I'm pretty sure you heard a lot of those in your career. We all did. This one is just such a rule. Take it for what it is. It should use about 1 cubic meters for every square foot of your facility. That should be your guidance. However, as I said, industrial facilities are fairly tricky, so don't take it as a gospel, just as a guide. You say, okay, am I over, am I under, where am I? Because all those things like internal heat gain, your facility operation, all of those, your need for internal air quality different than others, all of them will have an impact on that number. But as a good guideline, 1 cubic meter per every square foot of space is what should be given. So for our particular improved global facilities, it's about 200,000 square feet, 200,000 cubic meters per year. We use 461,000. So we're way over what we should be. This is worth investigating. You don't know what you're going to find, but at least it doesn't jive. It's worth your time to actually look at it a little closer than just saying, oh, well, we can't do anything about it. I can tell you that I have done a project a couple of years ago where we shut down about 300,000 cubic feet of air to the facility, and we saved almost 400,000 cubic meters of natural gas on 1.25 million consumption. So we saved almost 30% by shutting off exhausts. They had about 500,000 CFM of exhaust and 160,000 CFM of makeup air. So this exists. This type of mismatch between exhaust and makeup air really exists in the facilities. It's not outrageous. So now that we know where the energy is going, we know roughly how much energy we use in space heating, how much we use in makeup air, how much we get for free. Now we have an idea. Now we can start prioritizing our opportunities. Now we can look, okay, well, I know how much is used where. Let's prioritize the opportunities that I know exist. So we have 3 from before. I used the same idea. Infrared heating, somebody tossed out direct fired space heating. Somebody says, let's recover some heat of the process oven. So you had 3 ideas already. Now when you looked at the exhaust and you said, oh, wow, I'm losing 460,000 cubic meters as opposed to 200,000 cubic meters, maybe I can reduce exhaust. And maybe there's something else that I don't quite know, but I know 4 for sure. How to prioritize them? How do we say, okay, which one to do first? Which one makes the biggest bang for your buck? Because that's what you want to do. Often, heating and ventilation is last on the list of things that people in the facilities worry about. We all worried. You worried today. I used to worry when I was capital projects manager. Do I ship the product I told customer we're going to ship? Do I ship it in a safely manner so nobody got killed or maimed or hurt in our facility? And did I ship it at some sort of profit? Those are the things, and the quality control. Those are the things that we cared about. Heating and ventilation truly was not one of our focuses. I had 12 furnaces for processing steel in my facility. We paid $1 million a month for gas. We didn't care. If we didn't ship coils that we made, you know, the spring coils for cars, if we didn't ship them to Chrysler and we shut down their plant, it wouldn't matter how much I saved in energy. Trust me. We've done that once, by the way, in the 90s. They were not happy with us. So we all appreciate what your priorities are. So we want to start small when you're doing the heating and ventilation. Let's start with some smaller project, prove ourselves that we know what we're talking about, and then go on the bigger things. You don't want to jeopardize your reputation on going all out, replacing everything in your facility all at once, and then like, where is the money coming from later on? And you're like, oh, our calculations were a little bit off. So let's do one step at a time. Again, our ESCs are here to help you with this. If you need a sounding board, if you have 5 ideas, somebody's tossing at you, call one of us. Say, you know, guys, I've heard this guy is selling this. He's telling me 30% savings. Have you heard of anything about it? And we'll tell you, we are not affiliated with any vendor, and we have nothing against any of the vendors. So we'll tell you our honest opinion. We'll say, yeah, I know 3 other guys did that last year. They had great savings. One guy did it, he had so-so savings. The other guy did it, he didn't see any savings at all. Third guy did it, and he had like 30% savings. So we'll give you that information at no extra charge for you. It's just a sounding board. Just, am I on the right track? And now we're going back to a very important point that Victor has touched on when he asked about makeup air, how much makeup air, how much exhaust. So far, we have done our calculations just to get us in the ballpark. How much we use on makeup air, how much we use on space heating, how much we get for free from internal heat gain. We based all of that on information on nameplates. So my nameplate on this makeup air unit says 50,000 CFM. It must be 50,000 CFM. I had a customer who had 40,000 CFM, I believe, it was makeup air nameplate. We measured it, it was 30,000 CFM that they gave him out. They replaced a couple of filters. We got back to about 35,000 CFM. Okay. So the next step, when you identify opportunity, and that 460,000 versus 200,000 is a significant opportunity, then I would recommend doing a proper air balance of your facility. Why doing an air balance? To confirm, A, that your nameplate information was correct and you're working with proper CFMs, and 2, to find out, do you really need as much exhaust or makeup air as you think you do? So that's why when I recommend doing air balance, I usually recommend it done with not just somebody who does air balances, but somebody who's familiar with indoor air quality standards, because that's the second portion. Easy to shut down all the exhausts, but if you jeopardize your health and safety of your environment, it's not good. So you want to know, you want to talk to somebody who understands both sides of the coin. So what do you want to do with this? You want to effectively quantify what your airflow actually is. And not just airflow as it is today, but they want to talk to your facility guys, and they want to find out, do you operate all these exhausts in the winter and in the summer? Some of them only in the summer, some of them only in the winter? And the reason why that is important is because in my experience, and feel free to share yours, is most of these exhaust problems, over-exhausting, happens because in the middle of the summer, next to those process ovens, it's pretty darn hot. So what do you do when somebody comes from the floor and complains, I'm really hot here, I cannot work? Install 5,000 CFM exhaust right on top. Bore through the roof, get the production going, everybody's happy. But those are case-by-case installations, therefore they're not centralized. So what happens in the wintertime? Keeps running, because nobody bothers to go up on the roof and turns it off. So now you have, even though winter was okay to begin with, a little by little you have huge overexhaust, because Joe was complaining, Mike was complaining, Damir was complaining. There's all sorts of exhaust on the roof that nobody turns off in the wintertime when nobody's complaining. It's not an issue, but now it's just stayed there. Air balance would find that out. It would say, okay, you have all these exhausts. They were installed because of the summer conditions. Nobody's turning them off in the winter. It doesn't get any cheaper to save energy than to say, I don't need this exhaust running in the middle of the winter, turn it off. Doesn't need capital equipment, doesn't need any requests for funds. It just you're requesting your maintenance or yourself, however it works in your facility, to go up there on the roof and turn the damn thing off until the springtime. So that's what air balance assessment would do for you. Properly executed air balance assessment will cover all of these things. It will measure airflow, all of your airflows, so which means volume and temperature of each air input and outlet. Each one. It will check for indoor air movement. People come in and they do what they call a smoke test. They light up some smoke and then they film it across the facility, how that air is moving along. Account for seasonal variations, so they will ask people, do you operate this in the winter, summer, both, either? And they will take note of the existing equipment. Your filters are dirty, your indirect fire gas unit is stuffed up, you need to clean it. What that will do for you is significantly reduce your potential risk of your project that you put your reputation online for going wrong. It will say, yes, I'm now sure that my unit will save this much because I checked the temperatures, I checked the CFM, and those are only two inputs into the formula. So temperatures are given because that's your set point, and your outdoor temperature, there's no question about that. CFM you measure, there's no question about that. So your formula is pretty darn exact. We all work in engineering, we all work with estimates. Plus minus 10%, it's pretty darn good. That is what air balance does for you. And I often hear air balance, I don't have money, I can't afford air balance. Pretty sophisticated air balance for 200,000 square foot improved global facility would be in the vicinity of about $5,000 to $7,000. Considering you're going to be spending, say, $20,000, $30,000, maybe even $100,000 on your new equipment, that is a pretty safe insurance policy. However, because we're nice guys, we're going to launch a new campaign as of today, limited time campaign where we will cover 100% of the cost of your air balance. Okay. It's limited time, limited space available because we only have so much money to spend, so it's going to be first come, first served basis. Scope of work must be approved by one of our guys, and that's because there will be a lot of people who can measure your volume of air, but they won't understand what they measure. So often they will go around and actually turn on the fan that's off just to measure it because you told them to measure it. You want somebody who will recognize that and who will say, oh, you know, it's off. This is winter mode. So we want to be able to approve scope of work. Application forms for this particular campaign are due by July 1st, so you have to have application in by July 1st, and the project has to be complete by the end of the year. And your flyer in your package has more information on that air balance. So we have said that we have calculated the energy content in the air that we're exhausting out of the facility, which is directly proportional to the volume of air that we are exhausting, of course. We have internal heat gain that we can't do much about because that's our processes, our equipment. And the rest of it is metered seasonal load. Then we have makeup air that consumes a certain amount. So what we can really affect is this. This is the potential for your savings when you're reducing the exhaust alone and you're leaving the makeup air where it is. So your space heating. So in example of improved global facility, that's about 461,000 cubic meters is potential. So let's see how much we can actually save in this exercise. So let's say that we have done air balance study that we will pay for. And we found out that given your indoor air quality requirements, you can get away with 101,000 cubic feet per minute of air exhaust. So you reduced it by 75,000. Why 101,000? Because we got rid of the 175,000 CFM exhaust, and we have remaining 100,000 plus 1,000 of CFM of process oven exhaust, which you can affect, but that's not the purpose of this exercise. So we ended up with 101,000. So let's calculate, based on heating efficiency of 80%, and your average outdoor temperature 37.5, indoor 70 degrees F, let's calculate what's our energy content now in this exhausted air. So again, that's your exercise in one of your activity books. Formula is exactly the same as before, but instead of 175,000, now we have 101,000 CFM as an input. So we have all done our math, you and I together, correctly. We should end up with about 532,000 cubic meters of natural gas. Remember before that was 900 and something thousand, now with 500,000 cubic meters. As a follow-up to that exercise, we now take 532,000 cubic meters that we have now known to exhaust. And we know we have 229,000 of internal heat gain because we haven't changed that particular one. And we have makeup air consumption that was about 232,000. When we subtract all of that, and I'm pretty sure you have that as well there, but that's just a subtraction, you should end up with a space heating now requirement of 70,000 cubic meters. We remember from before it was 460,000 cubic meters. So these are estimated savings for our facility that we're working today. 390,000 cubic meters per year by turning off 75,000 CFM of air. And you have to remember, you still have almost twice the amount of exhaust than your makeup air. So in this particular case, our indoor air quality was not affected because we checked it. But whenever you do a project like that, I would recommend checking that before and after. But 390,000 cubic meters, that at say 25 cents, that's almost $100,000. That's not a bad savings for just effectively turning off units. It's pretty good. So let's go to heat recovery. If you remember, one of the suggestions that we got from peers, vendors before was to recover process heat, to take the heat of the exhaust of our process oven and recover it in the heating. But there is one heat recovery idea that is probably far easier to implement, that many people have already done, and many people should be doing it. And that's, most of us have air compressors in our facilities. In this improved global facility, we have two of them. One is the lead one is the lag one. They're situated usually somewhere on the side so we can get a lot of fresh air to them, so we can cool them, because what they do, they heat up really lots. So we cool them. But if we take example of 75 horsepower compressors, let's say they're identical because we have them as almost as a backup. One runs as a lead unit at 100% of the time. The other one runs at the lag unit at quarter of the time, 25% of the time. There's such a thing as a service factor for your compressors. Usually it's about 1.1, 1.15, which gives you your true brake horsepower. So your nominal 75 times one service factor, 1.1, gives you 82.5 horsepower. That's the brake horsepower. That's the actual amount of heat that you have to work with. So we already said these air compressors heat up a lot. If you ever stood by one, you will know that. Your air is, to compress air, it takes a lot of energy. A lot of that energy is converted into heat right at the spot, which is why those compressors are usually off-site, somewhere on the small room, somewhere close to the outside walls. But let us go through the exercise in this activity book. And let's try to calculate how much these air compressors generate in heat. Because you have to remember that air compressor, 80% of the heat, of the energy going into it is converted into heat that is just being rejected as soon as the air is compressed. So you take all that fresh air, you heat it really, really high, and then typically what happens, you have these little hoods above the compressors, and you dump that air promptly out. So if we do calculation, according to our activity book that you can quickly do, based on these parameters, this is what you should be coming up with. So for simplification, and because when you want to justify your projects, you want to be on a conservative side, let's just say you only have need for your heating for half of the year. In Toronto area, you will have longer than that, 9 out of 12 months. But let's just say it's half of the year that you can recover that heat. That means that all that available heat times 0.5 is the heat that you can actually recover in your heating process, in your heating of the facility. So if you follow that in the activity handbook, this is what you come up with recoverable BTUs per year. And at 80% efficient heating system, that would be equivalent of about 30,000 cubic meters in a heating season, so over 6 months. So that doesn't seem like a really big deal. But most of us will have more than 75 horsepower compressor. And when you think about it, what do you need to recover this heat? You need to put a hood that you already have, that you're taking in the outdoors. You put a damper in that hood, and you have another 20 feet of ducting, and you just dump that air into your that you're heating usually, so your shop floor. So investment is very, very low, and risk is non-existent. And if you take a look at 30,000 cubic meters, once we did the proper air balance, we reduced our exhaust. What was our space requirement, space heating requirement? 71,000, Josh, thank you. 71,000 cubic meters. We're recovering 30,000 of those with this one particular instance. So we are almost recovering half of our needs just by doing this. That's how you should be looking at it. Don't worry about actual cubic meters. Investment is low, risk is very low. Let's recover what we can. Just to be on the safe side, what you want to do is you want to check your consumption in the shoulder months, May, October, depending where your shoulder months are, to ensure that your space heating requirement in those months is still higher than the recoverable heat that we just calculated divided by the number of months, divided by 6. Just to ensure that all the heat that you dump into the facility will actually be used. So that's a very simple way of recovering heat that you cannot help but generate anyways, as long as you have air compressing system in the place. So this is what I was talking about. If you look at it here, effectively, you duct the heat of the compressor into the facility. That's the extent of your investment. It can be as simple as that. So that's one of the simplest ways of recovering heat. The other idea that you will hear a lot about, and you should be aware of, is what we call direct fired space heating. I know you can't read this, and don't worry about it. It was just there to prove that gas code has changed in the last few years in Ontario, and it allows for what we call direct fired space heating units, which means that you can take outdoor air, heat it directly in the stream of the burner, and dump it into the system as a space heater, which you were not allowed before. Only limitation here is if those are sleeping quarters. Not sleeping quarters when people sleep on the work, but actual sleeping quarters. So that has changed, and lots of people could take advantage of these units. So we'll just go over a simple calculation of how to look at this opportunity. So it pertains to the code B149-1. This one is from 2005, so it was in the code at least since 2005. It says that we can have non-recirculating direct fire unit, can be used as a space heater, or make-up air, or combination of the two. So effectively, you can take one unit and replace your unit heater and your make-up air with this. And downside of that is for people who recycle their air. If you have a recirculating units, instead of the 100% outdoor make-up air, you recycle some of your air, and you take, say, 90% of the indoor air, you go through the unit, and you add 10% fresh air, put it down. This one cannot do that. This one has to be 100% outdoor air. So if you have any method of recycling air already, this is probably not the best way of going, because any savings in efficiency will be offset by your loss, because now you're heating 100% outdoor air rather than recycled air. But there's plenty of opportunities for this kind of technology. So this is what they look like. This particular one is from Cambridge Engineering. There's a bunch of them out there nowadays, so don't worry about the name of the vendor. It's not meant to promote this vendor. It's just a convenient picture. And what you will typically see on these units on the nameplate, you will see maximum discharge temperature is 160 degrees F, and maximum temperature rise is 160 degrees F. That's the real advantage of these units. That's why you can use them as a space heater, because your typical make-up air unit, 70, 75 degrees, if you really push it, 80 degrees F is the temperature of the air entering facility out of that unit. This one is almost double that. This one will actually allow you to heat the space with that. So you can see all these unit heaters that we have in our facility. You have some of the radiant tubes, a bunch of them. All of them can be replaced by only a couple of those direct fired space heating units. So if you're building a new facility, I would highly encourage you to investigate this possibility. Instead of installing unit heaters and make-up air heaters, use that. In retrofit situations, it's a little trickier to justify usually, but it's something that you should be seriously considering. So let's go and calculate some more. So let's say that we have exhausted air energy content like we had from before, I exercised before. We have fixed internal heat gain, and we have space heating and make-up air unit that comprise our metered seasonal load. If you install these direct fire space heaters as holistically as possible, which means you look at both your make-up air requirements, your space heating requirements, this is the potential for savings. If you want to do it with the least cost, your potential for savings goes down, because you're leaving your make-up air as is, and you're effectively replacing your unit heaters with this technology. So your potential is smaller, and you'll remember that even if you did especially if you did your air balance, you're only dealing with 70,000 cubic meters of gas in savings. So your potential is much smaller. So you should look, if you do go this way, you should look at a holistic approach and say, do I need so much make-up air? How much is that? Can I replace the whole system with these new units, rather than bit by bit? So if we calculate this example in the book, I purposely made this different than the other examples. It doesn't follow chronologically. This is one of those cases where people will come in and will tell you, oh, I measured your air balance. You have 175,000 CFM or 176,000 CFM exhaust. You only have 50,000 CFM in make-up air. You know, you should really be balanced, so I'm going to install extra make-up air system to balance it. So instead of looking, do you need this much exhaust? Do you need this much make-up air? They'll just say, well, you have this much exhaust. I'll just add make-up air until it matches exhaust. That is not the best way of doing it. That's why you should be very aware of how much you actually need. So if you do calculation in your activity workbook based on these inputs, using same formula, you subtract the internal heat gain, and over a period of 4,300 hours, your savings will be only about 80,000 cubic meters. On 460,000, you're saving only about 80,000 cubic meters. Not a heck of a lot, especially when you consider the investment. So this is one of those things where you want to install the units as a whole system and look at the whole system, how much you actually need. Because potential, as gentleman here has pointed out, is great. It's measured. It's actually happened. We know it. So let's not waste a good opportunity and looking only at piecemeal applications. So one thing, technology that keeps coming back over and over is infrared space heating. Those are those tubes that people put on top of the usually shipping doors, shipping docks, because usually they're resolving a problem that is real. And that's the problem that people feel very cold when the shipping doors are opened, because there's an inrush of cold air into the facility every time somebody opens the shipping doors. Well, why? Nobody's asking why. That's because your whole facility is not balanced. If it can be balanced, do balancing first, then worry about how to heat this particular one area. Because radiant infrared space heating, low intensity, those tubes that we mostly see, works like this. You have a burner, you have some sort of blower, natural gas connection to the burner. You have a tube that acts as an exhaust for this burner. You have temperature control to control the speed of the blower, to control the natural gas flow. You have some sort of a shield on top of it, so the radiant heat is directed down. And you have radiant heat that is radiating out of those exhaust tubes. So that is what your radiant heater does. It transfers that radiant heat, instead of heating the air, it's supposed to heat the objects. That's where it comes from. The application comes from warehousing applications, where you have objects that need to be heated and not air, because there's very little movement of air in warehouses. So for that application, that's an excellent application for IR heaters. Localized heating, warehouses where there's not much movement of the air. But because we're heating not air, but we are heating the objects, you put infrared tube on top of the shipping doors, and you have highly imbalanced building, and you have onrush of air going through those doors. What does IR heater exactly do? Not heck of a lot. If you stand right beneath it, it's nice, warm. Guy standing 10 feet behind won't feel anything, and it'll be as cold as anything. So let's first balance the building. Let's make sure that we don't have that inrush of air unnecessarily. Then let's put infrared heater on top of it, localized, with some sort of logic behind it. And one thing that you have to also establish is, because infrared heater only worries about space heating, doesn't make up your air, doesn't do anything else, that's your space heating only, how much actually you use space heating. That's why it's important to do the back of the envelope calculation we just did on how much space heating is costing us, because that is your potential. So if somebody comes in and says, I'm going to sell you a heater, you're going to save 30%, that's that space heating part, that's 30% of that, not 30% of your bill. So be very clear about that. And the last idea that people have, and I've seen that before, to recover process waste heat. So we had that nice little oven. We had a stack. It goes up the stack. The heat, about 20%, let's say, of the heat goes up the stack, given. And we can recover that heat. There's ways of recovering that heat. Very good application once all other heat recovery options are implemented, because this is typically not the cheapest application you can do. If you have any dirt in that air, you have to be very careful how you select your equipment, because you will plug in your heat exchanger surfaces very quickly. You have to have proximity of HV equipment. For example, you want to preheat the air through the heat exchanger from the oven exhaust. You preheat the air for your makeup air unit. If your makeup air unit is 300 feet away, you will actually recover very little heat unless you have some really mega insulation. Because you're talking about usually 400 degrees F in these exhausts. It's not a heck of a lot of heat to begin with. The other problem that you have with that is that you only, as gentleman pointed out here before, you only recovering half of your potential. So if you do have process heat, you want to recover it, that's a great idea. Try to recover it back in the process somehow, because then you will use it all the time. you will just double your return on investment. With very similar investment strategies, it will not cost you a heck of a lot more to recover it back into the oven as it does to put it into an HVAC unit, but you will use it twice as long. So that's something that you should be mindful of. So now let's look at the overall facility one more time, the facility we spent the last couple of hours in. How do we prioritize it? Now we have all these ideas. We have infrared heating, direct fired space heating, process oven, all of these ideas that we have to work on. So we put down some sort of boundaries. We say how much it costs us versus the benefit. I am not going to do detailed calculation for a couple of reasons. One is because this is a fictional example anyway, so it won't do you any good. But second is each one of you has costs that are slightly different, and each one of you has a slightly different level of risk, how much you actually want to spend for what benefit. So I'm trying to do only qualitative comparison here. So more dollar signs, the more expensive it is, or more benefit you get. Less dollar sign, it's less costly to implement, and less benefit you get. So if you do comparison of all these things that we've done in this particular facility today, and you actually rank them, you will end up with something like this. So to be able to prioritize these opportunities, you need to know, A, how much you use today, so you know how much you can save, how much your benefit is. Then when you have this information, get a couple of vendors, get quotes, and say, how much would it cost me to implement this? And compare those two, then prioritize them. That's the best way of doing it. So in Improved Global Facility today, reducing exhaust was saving us about 390,000 cubic meters for very little investment. So that would be our priority number one. Let's resolve exhaust. Once we resolve that, then we can recover some heat of the air compressors, further reduce our space heating requirements. Then you would put some infrared heating judiciously, localized, where it really helps. For example, if you have any space that you use as a small warehouse, some room where you put materials and you don't want it to freeze and that's only what you do, put a small tube there. That's great. And then you go, if you can afford it, if this is a new facility, if you have to rework your whole system, go to direct fire space heating. In our calculation, it saved relatively little because that was this facility. If you were to pull everything out, do it properly, reduce your exhaust, and your makeup air matching them, then do direct fire space heating with some control systems, you would be saving much, much more. Then that would be, in that particular case, that would be number one option. The point is, you have to qualify it for your situation. And lastly, I would do process oven heat recovery, and if I can, I would recover it in the process itself. So those are the takeaways that I would like you to take with you today. I would like you to be able to go back and say, I can estimate roughly how much energy I'm using. This is my potential. Once I know my potential, now I can talk to certain people. You can talk to Enbridge guys who will come and check your calculations or do your calculations for you. If you don't have time for it, we'll do it for you. Talk to us about which vendors we've worked with, where to find this kind of technologies. And then you can implement and be successful in implementing this kind of thing. So I hope that by the end of this seminar, you have gained some understanding of how the facility actually operates. You have a better insight into the facility. That we helped you with this, knowledge development, opportunity identification, measurement, and engineering analysis. And it's up to you to have a very successful implementation. And we will help you along the way as well. We will, of course, for any successful implementation, we will provide you financial incentive that's directly proportional to cubic meters saved. And you can talk to either myself or any one of the ESCs that I would recommend to talk to about your particular applications. Thank you.